Have you ever really thought about how our world, with all its color and complexity and sound, gets crammed inside a machine? How a photo of a sunset or even just a thermostat knowing it's cold is even possible? It all comes down to translation, taking our rich, messy world and converting it into the simple, black and white language of computers. So look at this. On one side, you've got stuff that makes total sense to us. Charts, graphs, things we can understand at a glance. And on the other, one of the very first machines designed to read data. So here's the big question for this whole explainer. How do we bridge that gap? How do we get our world into the machine? All right, let's get into it. The first thing you absolutely have to grasp is that computers see the world in two and only two parts. Everything, and I mean everything, is either an instruction or it's data. Just think of it like really simple grammar. The instructions are the verbs. They're the action words. Add, save, copy, delete. But you can't just add, right? You have to add something. That something is the data. It's the noun. It's the numbers you're adding, the document you're saving. One is useless without the other. And here is the perfect real-world example. Your shopping list, milk, eggs, bread, that's your data. But the list itself doesn't do anything. The instruction is go to the store. See? The computer needs the command, go to the store, and the data, the list, to actually get the job done. So a computer gets its instructions and its data, but how does it actually read any of it? It can't look at a shopping list and read the words. No, it has to translate everything into its native tongue, and that's a language with only 2 words in its entire vocabulary. Which brings us to probably the biggest, most fundamental question of all. Why? Why binary? Why all the zeros and ones? We have a perfectly good system with 10 digits, 0 through 9. Why on earth don't computers just use that? Well, the answer isn't about math. It's about physics. Deep down, a computer is just a mind-bogglingly huge collection of tiny little electronic switches. And a switch can only be one of 2 things. It's either on or it's off. There's no in between. So binary, with its 1 for on and 0 for off, isn't just a choice. It's a perfect reflection of how the hardware actually works. And every single one of those ones or zeros gets a name. We call it a bit, which is just short for a binary digit. You can think of a bit as the single atom of the digital universe. Every photo, every song, every email you've ever sent is just built from mountains and mountains of these tiny little things. And just like atoms form molecules, bits group together to make something more useful. You put 8 bits together, you get a byte. Get about 1,000 of those, you've got a kilobyte. And you just keep scaling up from there to the megabytes, gigabytes, and terabytes that measure our digital lives today. Okay, that's enough theory. Let's make this real. We're going to do a live translation. We're going to put ourselves in the computer's shoes and decode an actual message sent from a digital thermometer bit by bit. Now, this table, this is our secret weapon. It's the dictionary that tells the computer what every single bit means. You can see each position in the code has a specific value. Some bits represent whole numbers, like 1 degree, 2 degrees, 4, 8, and so on. And other bits represent the fractions of a degree, a half, a quarter, an eighth. All right, here it is, the raw data, fresh from the sensor. Let's start with that first chunk, the part for the whole numbers, 00000101. So we look at our dictionary. We've got a 1 in the 4's place and a 1 in the 1's place. The rest are zeros, so we ignore them. So we just add them up. 4 plus 1 is 5. Simple as that. Now for the second chunk, the decimals, 01010000, we've got a 1 in the quarter degree spot, which is 0.25, and another one in the 1/16th spot, which is 0.0625. Add those 2 together, you get 0.3125. So we just combine our 2 answers. 5 plus 0.3125 gives us 5.3125 degrees Celsius. And there you have it. We just spoke fluent machine language. So that felt pretty clean, right? A perfect one-to-one translation. But the thing is, converting our messy analog world into these neat and tidy bits isn't always so perfect. And sometimes the absolute tiniest little mistake in that translation can be catastrophic. This is from a report on the Gulf War in 1991. An American Patriot missile system, one of the most advanced pieces of technology on the planet, failed to stop an incoming missile. And the reason for the failure wasn't a broken part or a mechanical issue. It was a math problem, a translation error. The entire disaster, every bit of it, came down to the system's internal clock being off by this much, just over a third of a second. How? How could something so small possibly matter? Well, here's how. The system's clock worked by counting tenths of a second, but the number 0.1, which is so simple for us, is actually an infinite repeating number in binary. Kind of like how 1 divided by 3 is 0.33333 forever, for us, the computer had to round it off, creating a microscopic error. But the system had been on for 100 hours straight. That tiny, tiny error, added up millions of times a second, had grown into a gap of 0.34 seconds. And that created a fatal difference between the real world and the computer's version of it. A Scud missile travels at almost 1,700 meters every second. In that tiny time gap, that 0.34-second gap, the missile had traveled more than half a kilometer. The Patriot defense system fired perfectly, but it was aiming at where the Scud used to be. It was aiming at a ghost. What a story like that really shows us is that this translation into binary is always an approximation. It's an incredibly useful one, but it's never truly perfect. And that makes you wonder, what else gets lost in translation? Seriously, just think about it for a second. Every song you love, every photo you take, every important document, all of it has been flattened, simplified, and squeezed down into nothing but an absurdly long list of on and off signals. It works, for sure, but it's not the real thing, is it? It's a copy, an echo. We just saw how a number as simple as 1/10 can't be perfectly represented in a computer's own language, and that tiny imperfection had deadly results. So that leaves us with this final thought. If a computer can't even perfectly grasp a simple fraction, what hope does it have with truly human concepts like justice or love or irony? What parts of our experience are we trying to translate that might just break the machine?